So this lecture on independent random variable. So this is on independent random variable. Independent random variable. Now we know what is independent event. We know two event A or B independent events independent if the probability of A intersection B is probability of A into probability of B. But what about if X and Y two random variable? Then what is the meaning of independent? So what the probability assigned? The definition is this. We say this is two random variable. We say X and Y are independent if, that means if and only if, definition is always if and only if the distribution function of the joint distribution function of xy is equal to just the distribution function of x into distribution function of y, and that should be true for all xy in R2 in R. Now the idea is actually this: so for every Borel set, that is for every Borel set, this equivalently for all Borel set A B belongs to A B is Borel, it's a Borel sigma German. This is Borel sigma German. R is real for random variable. For every Borel set, the probability of that X belongs to that Borel set A and Y belongs to Borel set B. This is the event. You know, this is the event. This is actually equal to probability of X belongs to A into probability of Y belongs to B. That is the X inverse of A and X, and X inverse of B. Probability of X inverse of A, that is the event. X belongs to A is the event. So this is equivalent. And for discrete type, so result is this: if X and Y are discrete type, discrete random variables, then X and Y independent if and only if, this is a theorem, if and only if the probability of X equal to X1 and Y equal to Y1 for a single value. A is a singleton set. That means it's just probability of X equal to X1 into probability of Y equal to Y. So it is just a probability mass function, the product of probability mass. That is the mass function, joint mass function X at the point XY is the product of the that is joint mass function of X into mass function of Y for all XY in. So this is the equivalent result for discrete case. Now what about a continuous case? For continuous case, so for continuous case, if X and Y are continuous, and another result is this: if X and Y are both continuous random variables, then x, y are independent if and only if the PDF, the joint PDF, now it is a density function, joint PDF xy, fxy is equal to the PDF of x into PDF of y for all xy in real life. So this is for discrete case. Now another corollary of this is if x and y are independent, random variables, then the conditional distribution x y given x for y x equal to x actually at point y, it is just equal to distributive function of y at y for all xy. And that for x given y at the point x, y x equal to y equal to y, this is just distribution function of x at x. For this is true for all xy. So these are all equivalent conditions basically. This corollary is not the equivalent condition. The other results are the equivalent conditions. So, and there is an important theorem is this very important theorem. If x and y are independent, and f and g, is random variables, are Borel measurable function. Let this is Borel measurable function. Borel measurable function. Then that fx and that gy are also independent. Proof we can see in any book like Rohatgi, just I omit the proof. Independent. Now, what about for the several n many random variables? So let x1, x2, x dot dot xn are random variables, n random variables, said to be mutually or completely. There is two concepts. One is called pairwise and it's called mutually. Pairwise means it is just pairwise. X1 with x2, x1 with x3, x1 with xn, x2 with x3, xi with xj, I not equal to j. So said to be for mutually it is different. Mutually implies pairwise, but pairwise does not imply mutually. Like mutually independent events. Pairwise independent event and mutually independent event are different. Now this all to call completely, also called completely independent if and only if the joint density function of x1, x2, xn at the point x1, x2, xn is just the product of all that xi's, all distribution function xi at the point x I equal to 1 to n, and that should be true for all x1, x2, xn, for all x1, x2, xn in real number. And what is called pairwise is every pair is independent. So and x1, x2 are called x1, x2 dot or xn are pairwise independent if for all I not equal to j, xi and xj are independent. So pairwise may not implies mutual. So but mutually independent implies mutually the result is mutually independent implies pairwise, but not the other way, not true. Now one result is if x1, x2 are xn are independent, and we have any subcollection of that, say xi1, xi2, these are subcollections. Say xik, these are subcollection. So this is a subset of this. Then this subcollection, that means x2, x7, x9, something like that. Obviously, k less than or equal to n. If k equal to n, then actually the equals that ik are independent. Now, one example that mutually independent pairwise may not be mutual. So consider this this three random vector, three dimensional x, y, z is random vectors with joint PDF, given by that probability of, this is a PMF, sorry, a joint PMF, not PDF. This is a discrete function, discrete random variable, joint PMF, probability mass function, x equal to x, y equal to y, and z equal to z. This is equal to 1/16 if x, y, z, these are belongs to this set containing 0, 0, 1, 0, 1, 0, 1, 0, 0, and 1, 1, 1. 3 ones or 1 ones. And 3/16 if x, y, z is 0, 0, 0, 1, 1, 0, then 1, 0, 1, and 0, 1, 1. So for 4 choice, there are 3/16, that is 12/16, and for 4 point, there was 1/16. So 4/16, total quality 1. Now this is pairwise, but not joint. Why it's pairwise? Now consider this probability of x equal to x, y equal to y. What is this? So x equal to x, y equal to y. So what is the value of, there are 8 many values total. So x, y, z can take 0 and 1. So this is 0, 0, 0, 1, 1, 0, and 1, 1. And all the probabilities are 1 by 4. 1 by 4. All the probabilities are 1 by 4. Why? What is 1 by 4? All these probabilities, all x, y belongs to this set. 0, 0, 0, 1, 1, 0, and 1, 1. Why this? So, okay, consider 0, 0. So, x equal to 0, y equal to. What is z equal to 1? Z equal to 1, it is 1 by 6. Z equal to 0, 3 by 6. So, sum of these two is 4 by 6. Sorry, 1 by 16, 3 by 16, total 4 by 16, so 1 by 4. Similarly, what about x equal to 0 and y equal to 1? Again, x equal to 0, y equal to 1, and z equal to 0, it is 1 by 16, and z equal to 1, it is just 3 by 16. Again, we add just 4 by 16, 1 by 4. So this is 1 by 4 for every choice, every 4 choice. Similarly, you can check and you can find that probability of x equal to x and or z equal to z is 1 by 4 for all xy in this set. I should not write for all. We just call this set as say S. And similarly, probability of y less equal to y and z equal to z, this is 1 by 4 again. This also, everything is 1 by 4 for y comma z belongs to that set. Now, what about probability of x equal to x? So it has only two values. So x equal to 0, y equal to 0, this is 1 by 4, x equal to 0, y equal to 1 is 1 by 4, so it has just half. And is actually equal to probability of y equal to y and probability of z equal to z, all are half. And just you can take only two values, x, y, z are either 0 or 1. Otherwise it is 0, and otherwise it is everything is 0. For every other value of x, y, z, this is 0. Now, that's why it is pairwise independent. So clearly it is pairwise independent because probability of x equal to x and y equal to y, it is half. So probability of x into probability of x equal to x into probability of y equal to y, it is just half into half, so 1 by 4. So it is equal to probability of x equal to x and y equal to y. So it is just independent. A pairwise independent. Therefore, x, y, z are pairwise independent. But it is not mutually independent. Why? It is clear. Because consider anything, say probability of x equal to 0, y equal to 0, and z equal to 0. So that is just 3 by 16. It is given, it is 3 by 16. But what is probability of x equal to 0? It is just half. What is probability of y equal to 0? It is again half. What is probability of z equal to 0? Again half. So it is just 1 by 8. So it is just 2 by 16. So not equal to 3 by 16. So therefore x, y, z are not mutually independent. Then we say two distribution are identical. The definition of we say x and y are identical, that is same, identical. We call identical independent IID. So in identically distributed if x and y have same distribution, have same distribution function. That is, the distribution function of x is same as distribution function of y. Sorry, that should be x, not y, for every value of x. For different x, if it is represents the x, intensity y is different, obviously. The The function is different, but the function is one function fx and another function fy at the for all x it is same. So for all x, that means the function is equal. That is this function are equal. Is a function they are equal. That's why identical. Now, one more definition is important for limiting theorem, limits theorem in probability, that we say that a collection xn is a sequence of actually sequence of is a countable sequence. It is infinite many x1 x2 x sequence of independent identical distribution IID independent identically distributed or IID random variables with common distribution or common law, sometimes called law, common law or common distribution. Say this law, common distribution is say this. If the distribution of x is another random variable and this is distribution of x with the same distribution as x, identical distribution with the x. That means xn and x are identical and xn's are independent. If this xn is an independent sequence, of random variables, and the distribution of xn is same as that of x for all I equal to 1, 2. So then it's called IID sequence. So one thing is very important. So this is important. Is this important note? Remember, the important note is this: x and y are identical. So it is identically distributed. If and only if they have the same distribution. Same distribution function. But it does not mean that x equal to y. Remember, the distribution is same. It doesn't mean that they are same. They're equal. Remember, it does not follows that x equal to y probability 1. Doesn't follow that x equal probability of x equal to y equal to 1. It may not be true. Like in the previous example. What happened? The probability of x equal to x is half with x equal, probability x equal to 0 is half, probability x equal to 1 is half. Probability of y equal to 0 is half, probability of y equal to half, 1 equal to half. Probability of z equal to 0 is half, probability of z equal to 1 is half. That means x, y, z are identical distributed. They have the same distribution. But not x equal to y. X may not be equal to y because there is a probability that x is not equal to y. Like that. the 0, 0, 1 say, or 0, 1, 0. In this case, probability of x equal to x, y equal to y equal to 1 by 4 for 0, 0, 0, 1. So x equal to 0, y equal to 1. That is probability 1 by 4. X equal to 1, y equal to 0. That's also probability 1 by 0, 1 by 4. That means probability of x equal to x is half, and probability of x not equal to x equal to y is half, and probability of x not equal to y is half. So x and y are identically distributed. Their distribution is identical. That doesn't means that x equal to y. It means, so in this example, probability of x equal to y is just half, and probability of x not equal to y is also half. So identical means not equal. Remember, maybe x is one value, y can take another value. So we say, so we have another definition. We say that x and y are equivalent random variables if probability of x equal to y equal to 1. So then we call it is equivalent, not equal distributed. It's called equivalent. So equivalent is something much big, much more than the identical distribution. So that means is equivalently say, the probability of x equal to a in any Borel set is same as probability of y equal to a for all Borel set A. Now, some other definition is this. Two random vectors, x1, x2, xn is random vectors, and say xm and y1, y2, y dot 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 yn another random vector. So there are two set of random variables. X1 is xm of the one set and y. We call this two different random vectors are random. Let this be two random vectors. Two random vectors we say they are independent. These random vectors are independent when independent if the joint distribution function of that x1, x2, xm and y1, y2, yn, that complete joint distribution x1, x2, xm and y1 dot yn is equal to the product of the, say we call it f1 x dot xm into a joint distribution of y, the random vector y. For that should be true for all x1, x2, xm, y1, y2, yn real number. So f is distribution function of that x1, x2 dot 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 xm, y1, y2 dot 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 yn, and f1 is the distribution function of x1, x2 dot 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 xm, and f2 is the distribution function of y1, y2 dot 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 yn. And the last important result is our theorem is this. Say there are two random vectors, say we call or we can say bold x, x1, x2, random vector x1, x2, xn and another random vector y, y1, y2, yn. This is x1, x2, x7, y1, y2, yn are independent. Let this be independent random vectors then what happened? Then each component, then xj and yk, j equal to 1 to m for all j, and k equal to, for all k equal to 1 up to n, are independent. Each component are independent, each from 1. X1 may not be independent with x2, but x1 is independent with y1. This y are capital Y, not the small y. It is a capital random variable, independent. Now, similar thing, if h and further, if h and g are two Borel measurable set, are Borel measurable set, sorry, Borel measurable functions, then that h of the function of x1, x2, xn and y, and that g of y1, y2 dot yn are also independent, Remember that h may be one dimensional or maybe multi-dimensional. So that function h may be the function from Rm to R, or maybe Rm to R, Rs or Rk. G also may be function from Rm to Rn to R or Rm to any other Rk, a Borel measurable function. So that h, x1, x2, xn may be a single random variable or maybe a random vector. So like say, if x and y are independent, then x comma x square and y comma y cube also independent. And if xy is independent with uv, then x plus y comma xy is independent with u square plus v square comma say u cube plus v, something like that. So this is a very important thing. One more remark, the last remark is this. This one more, the last remark. It may so happen, so it is possible that x is in x and y is independent, y and z are independent, oh sorry, that x is independent and x and y is also independent, x and z also independent. So x and y are independent, x and z are independent, but x and random vector yz may not be independent, and x and y may not be independent. That is important. So x is independent with y, x is independent, marginally independent with marginal z, but x is not independent with the jointly yz. That may so happen. That may be happening. But the other way is true, converse is true. If x is independent with y and z, the random vector yz, then x is independent with y and x is independent with z. But the converse is not true, that X is independent with Y and X is independent with Z, then X may not be independent with YZ, random vector YZ. This is important. And we can construct such an example where this happens. In next lecture, we just go through the function of random vectors. Say X, Y, Z are say random vectors. We then consider what is X plus distribution of X plus Y plus Z. What is distribution of X square plus Y square plus Z square? Something like that. We know the X, Y, Z are say normal independent IID normal 0, 1. Then X square plus Y square plus Z square is like chi square 3. We will go through that, the function of random vector in next lecture.